Okay. Thanks, Antonio, for the introduction. Thanks for inviting me. I'm very happy to be here, and it's an honor to represent my university and the Italian Statistical Society. Guido said that he was intimidated by the invitation. I'm scared, actually, by the invitation, okay? So I will try to present some results about Bayesian models for misreported count data. I will focus on some theoretical issues, but mainly on two applications. I believe I will be able to present just one application. No? No?
Sì, no, funziona male. Adesso, prova adesso. No, con quello di più.
Questo?
Sì.
Questo? Okay. Okay, that's the outline of my presentation. I will give a short introduction. Then I will briefly review underreporting models. Then I will focus on two data applications, CKD data. CKD stands for chronic kidney disease, and then fire data, which I will try to model the fire diffusion in the south of Italy, and then I will conclude with final remark. Okay, as you all know, data quality is emerging as an essential characteristic of all data-driven processes. We have experienced in the last years during the COVID pandemic that actually a major policy decisions were based on numbers of cases, deaths, testing capacity, and so on. However, as we all know, and as we have experienced, the reliability of statistical analysis strongly depends on the quality of the data. And this is particularly crucial in this period in which machine learning algorithms, as well as artificial intelligence techniques, produce very precise predictions or estimates. However, the functioning of this sort of black box strongly depends on what we put inside, so the quality of data we have at hand. In this talk, we focus on two mainly data sources, registry data and survey data. As we all know, survey data are a precious sources of information because they are accurately planned. And as we all know, we spent a lot of time in designing surveys, questionnaire, planning the sample size, stratifying the samples, and so forth and so on. Data are collected by experts or at least trained individuals. However, survey data are expensive in terms of cost and time. Registry data are a very rich source of information because they are based on the whole population. Think about census data, think about labor force data, for example, or sanitary registries. They are continuously updated and they are very low cost. However, data collection is very often not accurate, so we have misreported events. So in this talk, I will focus on registry data. And as we all know, data coming from official collection systems usually experience underreporting of events. Here there are some examples. Death-birth registry, especially in developing countries, it's very common to miss report of infants who die shortly after the birth. As a consequence, we have substantial underestimation of vital statistics, and as a consequence, government intervention policies are not adequate because of that. The other interesting application that might be very interesting, especially in the south of Italy, is about undeclared work. So it's very likely that labor force registry are underestimated, because we have a substantial fraction of individuals who are not going to declare where they work and how much they are paid. And the other topic is a topic of one of my research. It's very important for me to evaluate this kind of problem. That's the problem related to the violence against women. We know that the problem of violence is quantified according to policy reports, and policy interventions and allocation of funds strongly depends on police reports. However, as we all know, police reports are a substantial underestimation of the real amount of the phenomenon. So I believe it's our job to try to develop something to accurately estimate all these kinds of phenomena. All right, the talk will be based on these two papers. The first one has been published on biostatistics. It's a joint work with Silvia Polettini, my friend at the University of Rome La Sapienza, and the other names are medical doctors. And the second paper, I don't know if I'll be able to present it, is based on environmetrics papers with joint work with Alessio Pollice and Elsa Calculli. Okay. The motivating application, we start from CKD data, chronic kidney disease data. CKD is a gradual loss of kidney function. It's a very low progression disease. So we start with the first stage when the renal function is almost normal, and it decreases under stage 5, where actually the kidneys do not work. The decrease in functionality is measured according to the glomerular filtration rate and starts from moderate up to very severe disease when the renal replacement is necessary. It's a long life disease, so the patients need continuous therapy because they have problems in metabolic problems, so they have an imbalance of electrolytes, they accumulate waste in the blood, such as ammonia or uric acid. So they need transplantation and continuous therapies such as dialysis. CKD is a chronic disease. And since it's a chronic disease, as all chronic disease, it has a very strong social impact. Social impact means that it costs for the society, the cost for the society is particularly severe. Roughly 2% of the total budget of the healthcare system in Italy was spent for these kind of patients. And there are very interesting relationships between socioeconomic factors and the disease development. In particular, medical doctors believe that the progression of the disease can be somehow improved when the patients are able to access to nephrological care very early. Moreover, they believe that that's a strong relationship between socioeconomic status of the patients and the disease diffusion. And the other important fact that makes the CKD chronic disease is that it has a very strong impact on parents or caregivers that actually spend a lot of time, they have quality of life and need economic support. So the data are prevalence from the regional health agency in Apulia. It's my region. Apulia is in the very south of Italy, wonderful region. If you want to come, you are really welcome. Actually, what we have are counts from registry, patients enrolled in the hospital or regularly registered in the systems, and patients buying medicine with some medical doctor prescription that can be ascribed to CKD data, CKD disease. However, experts suspect that these crude counts of events are not trustworthy. So they believe that some patients are missing. So some patients living far away with other disease, with economic and social issues are not registered. And they also believe that some patients move to other regions for health care. And this is a very important problem, especially in the south of Italy, where we do not trust our sanitary system, so actually we migrate elsewhere. So they ask us to develop something to accurately estimate these counts. And what we did is to try to produce a model that allows to estimate this underreporting rate in order to have an appropriate allocation of funds and healthcare facility for CKD patients. The idea is that we have registry data, they are messy, so we can use survey data or auxiliary data to correct underreporting. That's basically the idea. So literature on this topic, let TI be the number of true events, they are counts, so conditionally to the mean parameter, they can model a Poisson distribution, where EI are the expected counts, so the number of exposed, and theta I is the event rate. And as usual, theta I can be modeled as function, whatever function of covariates xi and xp. However, we do not observe ti, but we observe yi, the counts yi, that are less or equal than ti. So our goal is to produce a model to estimate the event intensity θi, predict the true counts based on this yi. Of course, we are not the first literature dealing with this problem, even if the literature on this topic is not so rich. Usually, literature is very extensive in terms of measurement error in covariates, but when we deal with some kind of misreporting or measurement error in the response, literature is not so rich, not so many contributions. One of the main contributions has been reported in the paper of the Annals of Epidemiology of Bailey 2005. And the idea is that they extend the Poisson regression models using a censored Poisson regression model, assuming that the counts of the underreported areas are nothing but a lower bound of the true unobserved counts. In order to build this kind of model, they focus on the application of leprosy cases in the Brazilian region of Olinda, and they state that the underreporting is strongly correlated with the deprivation of each areas. So they define a threshold of the deprivation index, and actually this threshold is the base of the sensory regression. So all the areas whose deprivation index is below this threshold is censored and is considered as underreported. Otherwise, it will be not. Censoring regression does not account for the severity of the underreporting because they actually just censor the Poisson process, the Poisson distribution. And of course, in order to apply this censoring, you need a priori knowledge of a variable that should have a very strong relationship with the quality of the data. So you should have some experts information about that. In order to write down a model, as in many missing data model, you need that for some areas, you should have a completely observed sequence of data. This approach has been extended in a JASA paper of Stoner and co-authors in terms of compound Poisson model. The idea is that, again, Ti are the two counts that are conditionally distributed as a Poisson distribution with a relative risk θi, but Ti is not fully observed. So they say that, okay, since they are not fully observed, we can use a sort of data augmentation trick. So they define Wt as a Bernoulli distribution with parameter epsilon I, where this epsilon I is the reporting probability. So they state that yi, the observed counts, can be seen as the summation of this Wt for each area, and using the so-called Poisson trick, you have that if the yi are binomial distributed with upper bound Ti and probability epsilon I, and the true unobserved counts are Poisson distributed, then with a simple calculation, you can obtain that the marginal distribution of yi is a Poisson with parameter ei, θi, and epsilon I, where ei are again the expected counts. This is the standard definition of the compound Poisson model. Stoner extended this model by modeling θi, which are the rate, and epsilon I, that are the reporting probability, as functions of covariates. So the log of θi is a function of covariates x, and the logit of epsilon I is function of covariate z. In the paper, they also consider different kinds of functions. They compare polynomials, spline. However, the idea is that you can model this kind of parameters as function of covariates. They also add the random effects, vi and ui, that may account for spatial as well as residual variability. So they make the model a bit more flexible. However, that's our nightmare. When you try to apply or you try to develop a model, the problem is the model identifiable? Of course, these models are not identifiable. because the parameter is based on the product of theta I and epsilon I. So you need, so the likelihood is actually the same when the product is the same. Just to, the identifiability in the Stoner model relies, since theta I and epsilon I are function of covariance, the identifiability of the models, this model is related to the identifiability of the two intercepts, beta 0 and gamma 0. When the variables, when the covariates are standardized, gamma 0 represents the overall reporting probability, and beta 0 represents the overall rate, okay? So the identification in the Stoner model reflects on the identification of these two parameters. To assure the identifiability, it's necessary to introduce some constraints or some external informations. Different solutions. The first solution is being used in many papers and resort to a validation data set. So it actually means that we have an external source of data that might be used to correct the estimate. That's an idea that is widely used even in a small area estimation when you have the procedure of benchmarking. So you have a reference data set that you use to rescale the estimates. But as we can understand, the validation data sets are very rare, especially in practical applications. So in our application, we don't have validation data sets, so we cannot use this kind of solution. The other idea has been proposed by Moreno and Giron in JSPI paper. So they say we are Bayesians, so we can directly model the uncertainty about the reporting probability by specifying informative priors on each of these parameters. However, even this approach is very hard in our application because specifying epsilon I for each of our areas actually means that we know the quality, we have strong information about the quality of the data in each municipality. And it's quite hard because if you deal with a larger scale of data, think about regional data or even province data, you might have an idea of the data quality. But when you deal with the small municipalities, it's very hard to specify informative prior for each of them. Stoner proposed to assure identifiability according to these two conditions. So they stated that, they proved actually that identifiability is assured when X and Z are different, where again, X are covariates for the event rate and Z are covariates for the misreporting. And they are different, so they are disjoint sets, so they don't need to be orthogonal each other. They might be somehow correlated, even if they prove that the more correlated they are, the more variable the estimate will be. And the other condition is to use informative prior distribution on the mean reporting rate, so on beta 0. And that's, again, might be a good idea, especially when you have you have information about the overall diffusion of the disease on the whole territory. The other paper that focused on this topic is the paper on De Oliveira et al. 2022, published on Bayesian analysis, and one of the authors is Raffaele. And the idea is that they extend the compound Poisson model using a clustering idea. So they say the areas, each of the areas on which you have counts can be grouped in K groups, in K clusters. These K clusters should reflect the data quality. And this is quite an interesting trick because instead of estimating M epsilon I, you estimate just a subset of them. So they say that they define a clustering indicator, let's say HI, and this HI is a vector which is that helps in the definition of the cluster index. Indeed, they say that epsilon I is 1 minus HI transpose gamma, where gamma is a parameter lying in the 0-1 interval, and it's constrained to be less than 1. So for each area, this HI must be a priori specified and reflect the clustering structure. It means that For the areas with the highest level of data quality, HI is a vector of 1 and all zeros. And as a consequence, the reporting probability is 1 minus gamma 1. Instead, for the areas with the worst data quality, HI is a sequence of ones, and the reporting probability is 1 minus the summation of these gammas. So in this way, they are able to build cluster and to build reporting probability in an increasing way. They proved that in order to be identifiable, this approach only requires information about the reporting probability on the best areas. So it should be informative on gamma 1, actually. And it's very nice that epsilon can be easily interpreted in this approach because, again, it's a reporting probability. And they also derive a Jeffreys prior for gamma with a lot of mathematical efforts. So our proposal, actually we have a problem because medical doctors were not able to state us which variable, how many clusters. So we don't know in our application how many clusters we have in terms of data quality. So we are not able to assign each municipality to a data quality cluster. And we have another problem that so we cannot define K, the number of clusters, and we neither are able to define HI, so the variable defining the cluster to which each area belongs to. So our idea, quite simple, let's say, is to say, okay, the number of clusters cannot be a priori defined, and we might use an area clustering algorithm based on a proxy of data quality through a probabilistic mechanism. So the idea is to propose a Bayesian non-parametric model based on the initialized process that actually allows us to properly estimate underreporting probability, as easy as it is. So the model is the same we have sketched before, with the exception of the last step, where the reporting probability are clustered according to a non-parametric process involving covariates Z, where again, these covariates are a proxy of the data quality. I know that you know much better than me all these stuffs about Bayesian non-parametrics. However, within the wide class of predictors-dependent stick-breaking process, we rely on the JASA paper of Chung and Danson, and we define G of Z in this way, as in the equation 2, where the weights are obtained through normally distributing random variables Z transpose gamma, rescaled in the unit interval via standard normal CDF, and we denote with Cj the Dirac measure, and this measure does not depend on covariates, otherwise we have a problem of identifiability. Again, the variable Z that we use for clustering is a proxy of the data quality. The sequence of atoms is constructed introducing by a partial ordering, and this partial ordering is induced by defining the prior distribution of G0, and G0 is the uniform distribution defined in the interval A0, B0, and so forth and so on, with the constraint that Cj should always be smaller than C1. The choice of A0 and B0 should reflect the prior information about the best reporting area, and using actually the results in the Oliveira et al., we show that under the characterization of area, in order to identify the model, we only need to specify an informative prior with respect to A0 and B0. We have just to specify these two extremes in order the model to be identified. Other priors, standard approach for the other parameters, okay. All right, simulation study. Of course, I'm not showing all the simulation study because if simulations do not work, they are not going to publish my paper, so they work. So I'm not going to, again, to sketch everything, but just the main idea of the simulation study. So we've seen that if you have a larger proportion of areas with high reporting probability, the method in De Oliveira works almost perfectly. The problem is that you have the small number of observation in the best data quality areas. So when you have a very small amount of areas with very good data quality, the proposed model seems to be a little bit more robust. But the problem is mainly on the use or the definition of the Z variable, the data quality variable. When the variable you choose as data quality variable, as data quality indicator is a weak proxy of the data quality, the model in De Oliveira actually is not particularly robust because you cluster a priori, you should choose some kind of cutoff value to define which area are the best areas with the best quality of the data. So when you have a weak proxy, our model seems to be more robust with respect to the other approaches. And the other important message is that when the reporting probability is very low for all areas, whatever model strongly deviates for the gold stuff for the reference model. So whatever estimation fails. So if the quality of data is very, very low, whatever model do not work. Okay, some results, CKD data. Which kind of covariates? We use covariates about demographic density, aging index, unemployment rate, and the percentage of house ownership. The last two variables reflect somehow the economic well-being of the populations, and the first two, the social well-being. And one of the most difficult parts is to choose which variable might be a proxy of the data quality, or the reporting quality. Medical doctors tell us that the difficulty to access healthcare facilities are considered as a barrier to detect and notify events. That's why we use as proxy, data quality proxy, a variable measuring the minimal travel distance between the center of each area and each specialized health facility. According to that, we estimate the model with MCMC machinery, and we obtain these estimates. So we obtain that age and unemployment rate have a positive effect on the incidence of the phenomenon. That's quite normal. However, house ownership, that's the last variable, has a negative effect. So in those situations where you have a sort of economic well-being, the diffusion of the disease is slower. And that's the new map. On the left side, you have the observed counts. On the right side, you have the predicted counts, the predicted risk. And there's quite a difference in the color. Now, I don't know how good you are in geography, but I live here. That's Lecce, this point here, very, very south. And here you can see that colors are very different in Foggia, in the north part of Apulia, and here in Taranto. Why in Foggia? In Foggia, there is a substantial underestimation of the cases because many of the municipalities located here they are the mountains, okay? So it's very rare, it's very hard for people living here to reach healthcare facilities from a geographical point of view. Moreover, this area here is characterized by the fact that they do not have trains and public transportations are not so good, okay? The other way around, if you focus on Taranto, we all know that Taranto is one of the most deprived areas in Italy, and it's one of the areas in which the pollution is really important. So maybe this underestimation is due to the fact that there are so many diseases, so many other diseases related to pollutions that maybe even CKD disease could be related to pollution, but we still don't know. We don't have empirical evidence of this fact. All right, Antonio? Okay, so to conclude this first part, registry data are a precious source of information, maybe somehow, in some sense, neglected, okay, in our field, but they might contain very important information. So we propose a method for correcting underreporting of registry data using ad hoc proxies and extended compound Poisson model. We believe that our proposal can be a flexible alternative with respect to the alternative present in literature, at least when we don't have strong prior information about the reporting process. Just to sketch the other idea, the other paper very, very quickly, here the problem is about wildfires in the south of Italy. So we know that in the last periods, we have a large occurrence of magnitude of wildfires related to a number of factors. But the problem here, again, it's a problem of misreporting because the data have been collected using imaging spectroradiometer with 1 kilometer spatial resolution. So you count, okay, from a sort of satellite data, and you count the number of fires during the summer season. But here, what's the problem? These are the covariates. The problem is that what we observe is measurement error in count responses that might be positively inflated. So because of high temperature zones or small localized fires, we might collect signals that in practice are not real wildfires. But also we might have negative inflation because if it's cloudy and it's raining, the instrument is not able to count properly the data. So actually what we have are data that are inflated positively or negatively. So the idea is that, again, we have observed counts Y star through unobserved counts YI, and they can be modeled in this way. Since we have many zeros, we use a zero-inflated approach, but the idea is that we might use the count, we might model the count as Poisson distributed. Okay? However, what we observe is YI star, which can be seen as the sum of YI plus an add-in error and a leave-out error. So here we have two possible sources of errors. Again, if you use hierarchical model as sketched here, you can somehow estimate these two components of add-in and leave-out and obtain a proper estimation of the incidence of the phenomenon. What's the problem here is how to choose covariates C. Okay, we proved that the marginal distribution of Y star is given by these nice mixtures that accounts for the two parts of errors. So we prove that the model can be identified if you specify a proper distribution of the vector, of the parameter vector. And in the end of the day, we obtain, okay, a new map. So what we prove is that some use of local agriculture are not good for quantifying the phenomenon. So the impact of percentage of heterogeneous agricultural land use impact negatively of the probability of the fire presence. We have a negative effect of the number of rainy events, of raining days. And again, we have a positive effect of the presence of forests on the land. So when there are many forests, the probability of observing wildfires is lower. Okay? So actually, Gelman states that measurement error can be seen as a missing data problem and as a sort of unintentional missing data problem. So all the approaches I present actually can be rephrased in a missing data framework. When you have mismeasurement error, you need to accommodate the problem, otherwise the inference will be severely biased. And another problem with this kind of models is identifiability, that again needs of important prior specification. The other problem that we had with the practitioners is we implement our model, we write down all the code for MCMC, for estimating everything. However, you need to make life simpler even for practitioners. So one of our efforts was to produce a package, an R package, allowing practitioners to estimate these kind of models, making everything computationally feasible. And again, thank you.
Thank you, Serena. Is there any question from the audience? Okay. Curiosity, Brunero.
You reported the data for each single municipality in Apulia, but I wonder whether the data are collected at the same level of granularity, or maybe there is some
No.
higher agency that collect data from the province or from some.
No, they are collected at the same level. All data, all variables are collected at the municipality level.
So there is no spatial effect in the measurement error.
No.
Not in the phenomenon.
No, that's why we only use covariates collected at the same level of the data. So the spatial effect is just to exactly.
I have a curiosity, me too. Thank you very much. Guillermo did most of the work of the paper that you mentioned. But if I remember correctly, one of the big issues that we had with the algorithm is the convergence of the gamma. So I remember that we had to work a lot. So I'm just wondering if also in your experience you have this problem. And another question is this one. If I remember properly, it was very difficult to understand which variable was the proxy for underreporting. In our case, we had to speak with people at Brazilian ISTAT to understand that illiteracy was a good proxy. So how did you work in practice in this regard?
Actually, we also experienced the same problems in convergence of gamma zero, but when you scaled the covariates, we standardized after standardizing, okay, the covariates, everything seems to work a bit better. With respect to the proxy, that's a crucial question because it's very hard even to understand which variable explain the event rate and which variable explain the reporting rate. So it's very difficult to separate these two parts. Actually, we are experiencing this problem with violence against women data because it's very hard to understand which variable impacts the amount of the phenomenon and which variable impacts the reporting. So the probability that a woman going to the police to report the event. So it's very hard to split these two kinds of sets. Actually, you prove in the paper that it's not necessary to be completely uncorrelated. So we don't need orthogonality. So some variables may be used in both parts of the model. However, here we try many variables, but medical doctors are really strongly convinced on the fact that was a matter of distances. So actually this distance works well. Otherwise, there might be a number of variables that can explain the phenomenon as well. So it's not a job. I agree with you.
I do have a question. So how much the uncertainty of your estimates depend on the Poisson assumption in the first case particularly? Because I assume that those counts are actually under dispersed.
Sí.
So Poisson, it's useful, it works, but may have some issues. So I wonder this over dispersion that you induce with the Poisson model, if it has any effect on the posterior estimates of the parameter.
Yes, it might be. We also compared the Poisson model with the negative binomial model in order to account somehow for this under dispersion, but actually we come up with very similar results. A crucial role in these terms is played by the presence of random effects. So when you include the random effects, the effect of over dispersion is more is less important. Okay, so even if you compare, we compared with negative binomials and other kind of model, but we obtained very similar results. So I believe it's an issue, but in this application, it's not. Even the simulation study, it seems to do not impact because of the presence of random effect. If you remove random effects, even in the Stoner paper, you have very large effect.
But you have like a wider intervals, but the estimates should be roughly the same.
Exactly,
Okay.
exactly.
There was a question down there.
Nicola.
Thank you, Serena. A very, very good paper. I appreciate it a lot. I have a general question. So the idea is that you don't
Difficult ones, okay? General questions.
you don't trust the data from the administrative source. And the idea is that the problem is underreporting. But actually, you can have overreporting in that case, because if you are collecting data for administrative purposes, in some cases, you want to report more. For instance, for getting more money, because they say there are more cases, I want more money from the state. So the point is that your model is fully concentrated on underreporting. And I'm just wondering if you think that it can be adapted to the case where you have also overreporting.
Yes, I think so. Actually, in the second paper, I didn't show completely. Here, the problem is the one you said before. So the response variable might be miss or over or underreported. So the evolution actually of the model presented in the first part is this one, where the response variable is given by, here it is, given by the summation of what I observe plus an over-reporting, a DIN error, plus an leave-a-one error. So you can model. Again, here it's very hard to choose covariates. So in theory, everything works. But choosing the covariates in a real data application, it's really very, very, very hard. But of course, you can adapt. So here, in this paper, we propose this approach for ecological data, wildfires, but it's the same you are stating.